At the distance of the galactic center, at an angle of 1 arcsecond, an angle of 1 arcsecond corresponds to a length of 8,000 AU or 0.04 parsec. In the V band, there are 28 magnitudes of extension between us and the galactic center, which pretty well rules out observations at visible wavelengths. However, at infrared wavelengths of about 2 micron, there are just 2 magnitudes of extinction. Adaptive optics permits viewing the galactic center at infrared wavelengths with a resolution of 0.1 arcsecond. This permits us to resolve structures as small as 800 AU at the galactic center. The stars in the infrared are mostly cool giants. The stars you see in the infrared are mostly cool giants. If we assume that the ratio of giants to main sequence stars is the same at the galactic center as in our neighborhood, we deduce that the number density of stars within a parsec of the center is about 10 to the 7 stars per cubic parsec. For comparison, the number density of stars in the solar neighborhood is 0.1 star per cubic parsec. Now, at the center of our galaxy, there is a strong radio source called Sagittarius A. The total region of radio emission is about 50 parsecs across. The spectrum of the radio emission indicates that it is synchrotron emission produced by relativistic electrons accelerated by a magnetic field. The early radio observations that detected Sagittarius A were of low angular resolution and merely revealed the presence of an unresolved blob of radio emission. More recent observations have found detailed substructure in Sagittarius A. If we zoom in on the high surface brightness region of Sagittarius A, we find an interesting radio source called Sagittarius A West, which is a rotating mini spiral partially ionized gas about 5 parsecs across. Its radio spectrum looks much like that of an H2 region in which gas is excited by a central source of ultraviolet light. In the case of Sagittarius A West, the central source must be very luminous. But if we zoom in on the center of Sagittarius A West, we find a highly compact radio source called Sagittarius A Star. The angular size of Sagittarius A Star has been measured using radio interferometry. At the wavelength of 7 mm, the measured diameter of Sagittarius A Star is about 0.8 milliarcsecond, corresponding to 6 AU in physical units. The high angular resolution provided by radio interferometry also enables a measurement of the proper motion of Sagittarius A Star. Sagittarius A Star is an X-ray source as well as a radio source. The X-ray emission from Sagittarius A varies significantly on timescales of less than 1 hour, revealing that the majority of its X-ray emission must come from the region less than 1 light hour or 7 AU across. So Sagittarius A Star is a very luminous, highly compact source of radio and X-ray emission located at the galactic center. The leading hypothesis is that Sagittarius A Star is a supermassive black hole that is accreting gas. A supermassive black hole is a black hole larger than would result from a massive star collapse alone. The lower boundary is a bit fuzzy, but about 1 million solar masses would be the lower boundary of a supermassive black hole. Now, the black hole hypothesis is testable by looking at the motion of stars in the vicinity of Sagittarius A stars. If there is a black hole present, with mass much greater than that of a stellar mass, then stars in elliptical orbits around the black hole will obey Kepler's third law. Now, one star in particular, called SO2, this one here, has been observed to have a very small orbit with semi-major axis of about 900 AU. The orbital period is about 15 years. Now, the mass of the black hole given by this Keplerian orbit is about 4 times 10 to the 6 4 million solar masses. Since the star mass within about 0.2 parsecs of Sagittarius A star, all the stars are on Keplerian orbits, indicating that their dynamics are dictated indeed by a single massive object at the center. Combining all the orbits of stars near Sagittarius A, if you do this analysis, this Keplerian analysis for all stars, you find a mass of about 4 million solar masses for the black hole in the center of the galaxy. One of the stars, SO16, has an extremely eccentric orbit of eccentricity 0.976. At pericenter, it comes within 45 AU of Sagittarius A star. Since the star's orbit is neatly elliptical with no detectable deviations from the Keplerian orbit, the massive object it is orbiting must be spherically symmetric with a radius less than 45 AU. The only way that we can cram 4 million solar masses into a volume that small would be to make it into a black hole. The Schwarzschild radius of a black hole of mass 4 million solar masses is about 0.07 AU, which subtends an angle of 9 microarc seconds as seen from Earth. The radio and X-ray emission that we see from Sagittarius A star comes from outside the Schwarzschild radius of the black hole, by definition. These are observations that are being collected for over 10 years of stars in the galactic center to show that indeed what lies in the center of the Milky Way is a supermassive black hole. This discovery was awarded the Physics Nobel Prize of 2020.